So our first speaker will be Dr. Andreas Ruschhaupt. Andreas got his PhD back in 2001 in Germany. He spent a few years in Spain and then back in Germany before joining us last year in 2012. And Andreas, just go ahead.
Great, thank you. Thanks a lot for the very nice introduction. I would also like to thank the organizers for giving me the opportunity to present here a little bit of my work, to give you a little bit of insight what we are doing here at UCC. Okay. So where's my presentation? Okay, my talk will consist, it has a title, Control of Quantum Systems, so it falls in the second part of topics which students are interested in, apart from astrophysics, which I've learned a few seconds before. And my talk will consist of 3 parts. It's about control of quantum systems. So in the first part, I will give you an example of a quantum system. And these are ultracold atoms. How to get them? This is the big question. In the second part, I will tell you, if you have them, why do you want them? What can you do with them? And not only just, oh, it's good to have them, but there are real applications, and I will show some of them to you. And the last part is the main part. This is really about controlling quantum systems. This is what we are also doing here, theoretically, develop new methods to control quantum systems. But let's start with the first part, an example of a quantum system, ultracold atoms. Just start with, I would like to give you a little bit of feeling what means ultra cold. You all know this room has a temperature of roughly 20 degrees of Celsius, but we want to go to much colder temperatures. Well, if we cool everything down at 0 degrees, water is freezing, nobody here is surprised. Minus 19 degrees is the coldest outdoor temperature which has been in Ireland. If you go to Germany, it's a little bit colder. There the record is minus 45 degrees. So you're very lucky here. It's a little bit warmer here. Okay, let's continue cooling everything down. At some point, alcohol is freezing. And there's one mark, minus 273. This is practically the lowest temperature you can get with methods like the refrigerator in your kitchen. So with a cryostat, which is practically like the refrigerator in your kitchen, you can get these temperatures. But this is still far away from the absolute zero. Well, far, okay, it's a little bit here, but still it's an important difference. And just to remind you, well, you all know, why is there an absolute zero temperature? Well, because temperature is nothing but motion. Motion of particles. That means if it's warm, the particles are moving a lot. Here you see the Maxwell velocity distribution. It's a broad distribution if you have warm temperature. In a cold setting, all the particles are moving less. The Maxwell velocity distribution is more narrow. And this corresponds to cold temperatures. Well, if temperature is nothing but motion of particles, there's clearly a lower bound of the temperature, namely if all particles are at rest. And this corresponds to exactly to this minus 273.15 degrees Celsius, or to make it more simpler, this is simply 0 Kelvin. This is the beginning of the temperature scale. You all know also there's this Nernst theorem, the third law of thermodynamics, which tells you you can never reach really exactly the absolute zero, you can only approximate it. This you can also show, it follows from quantum mechanics, from the uncertainty relation. You can go only as close as possible, but never reach it. So where are we now? We are very close to this absolute zero. And to see it, really, you have to zoom in here. This is some logarithmic scale. And we are working roughly, we want to go to this limit of 1 microkelvin, or the particles are moving only with approximately 2 centimeters per second in the mean. This is the regime of ultracold atoms. And the first question is how to go there, because the usual refrigerator principles doesn't work anymore. And the key point is to do laser cooling, to use light to cool this. I don't have, unfortunately, time to go really here into detail, but for this, Kointanucci and Phillips, they got the Nobel Prize. And really, you have to shine laser light, which has the right frequency on atoms, and then the laser light is not heating the atoms, but on the contrary, you can really use this idea then, this setup, to cool the atoms. And by these methods, you can really cool the atom down to this 1 microkelvin. If you do it theoretically, maybe everything sounds simple. If you really want to do it in some laboratory, it's much more complicated, as you can see on this picture here. But nevertheless, why do you want to have ultra-cold atoms? Well, because if you have these ultra-cold atoms, the quantum properties, they start to play a role. If you have very hot atoms, they behave practically like billiard balls, like classical particles. But if you cool them down, then you see their motion is then described by the wave packet. They show really some quantum behavior like interference, constructive, destructive interference, and things like that. And in addition, if you have these ultra-cold atoms, it is possible to control the internal state of the atoms, because as you all know, atoms, they have some internal levels, you can control them. And it's also possible then to control really individual quantum systems. And this controlling of individual quantum system, it's interesting because when Schrödinger and Heisenberg and they all invented the quantum mechanics, they had the thought experiment. They were thinking like, oh, let's assume we have one particle. This is an equation for one particle, but for them it was sure nobody can really control a single particle. You only have beams, many particles. But nevertheless, it turns out now it is really possible to do this, what they only were thinking about. They had never assumed that it would be possible at some point, but today it can be done. And last year, there was really the Nobel Prize given to Haroche and Wineland exactly for this, for controlling individual quantum systems. And just, okay, we will stay here at this range of ultra-cold atoms, but maybe you ask, well, what happens if we go down, if we cool more? To do it, you need another technique, evaporative cooling. So the laser cooling brings you until this point, but here everything breaks down. You cannot cool it further because of the recoil. But there is another technique, evaporative cooling, and then you can get even to this point. Well, you ask maybe, why do I want this? Well, something happens here, which was predicted theoretically long, long ago, called from Bose and Einstein. That's why it's called Bose-Einstein condensate. And there you have a special behavior of the matter, because if you have a lot of particles, they all behave the same. You have one wave function describing all the particles. You have a big matter wave. And this was also in 2001. There was a Nobel Prize given to Cornell, Ketterle, and Wieman for really producing this condensate. As I said, this is only a little bit an outlook. We will not go to these temperatures. We will stay at the level of the ultra-cold atoms. But just to give you, you can even cool down even further. So we have ultra-cold atoms. What to do with them? Why do I want to have them? One advantage of ultra-cold atoms is, for example, to use them in metrology. Let's assume we have an atomic clock. You can have an atomic clock. This is a picture of one in Germany. And this one is working with hot atoms. And with hot atoms, you get only an accuracy of 1 second deviation in 3 million years. Well, okay, this is still very good. I agree. It's much better than all of our alarm clocks we have on our arms. But okay, still, nevertheless, this is in some way the limit. And but how can you do it better? Yeah, you read it here. You take ultra-cold atoms, which move slower, where you can control much better the velocity. And with them, you get 1 second deviation in 30 million years, which is a factor 10 better. And why do you really need this? Well, for the usual appointments during the day, it's maybe not so needed. But for example, if you want to study if the fundamental constants in nature, if they are really constant. If you want to measure deviations of them, for them you must be able to have very good standards really to check these questions. So this really makes sense to have a very good, precise time standard. But there are more applications of these ultra-cold atoms. One big field is this quantum information processing, where the key idea is, if you have a classical computer, you have a bit. Could be 0 or 1. Everybody knows it. But if you have a quantum system, there can be also superpositions of this 0 state and the 1 state. Every linear combination of them is a valid quantum state. And this additional freedom can be used for do computations much faster than you can do it on a classical computer. And this is a big power because you have this possibility in quantum mechanics of these superpositions. But they are also much more practical, even today, practical applications. One is this quantum crypto application or quantum key distribution. And there, the idea is you want to encrypt your message. Just a classical message. Well, we all had this NSA scandal now, and so you want really to send something which is absolutely safe. And you want to have it secure with the security of a law of nature. And this you can really do using some quantum systems to encrypt your message. And this is a field of quantum key distributions. Again, unfortunately, I don't have time to go into it, but just to tell you from one point to another point, the devices you can even buy today. There are companies, so this is a picture of one company of the catalog. You can go there, I want this device. But nevertheless, there are even much more directions where this field is going today. For example, there was some articles in the Physics World in September. One idea is to go to cell phones, to these mobile phones, to use this quantum cryptography in these mobile phones. Or to go to the quantum cryptography to multiple users, not only from here to here, but you have a network where you want to send messages. So this is a field where really this quantum mechanics is very close to applications, and it's some of the things you can really buy in a catalog. You just go to the internet and order it. And another field is, which is also very big, very important, it is quantum simulation. What is the idea here? This goes back to Feynman long, long ago, and you want to simulate a quantum system. And on a classical computer, it may be too complex, too complicated, takes too long time. Nevertheless, maybe it's much faster if you use another quantum system to simulate the quantum system you want to know something about it. This is a very simple example. You want to simulate some solid state object. How can you do it? Well, with light you can build, for example, optical lattice. So this is not a solid state thing. This is just a lot of traps for atoms, you can use this to model then solid state systems. As I said, I will not go here into detail because of time reason. This is just to give you a little bit of flavor about, if I have these ultracold atoms, what am I really doing with this? And nevertheless, I think it's clear for all these fields, metrology, quantum information processing, quantum key distribution, quantum simulation, it's very essential that you know how to prepare, manipulate, and control the states of your quantum system. And you have to control this with high fidelity, that means with high precision. You really want to end there. You want to have this state at the end, what you really want to have. And it should be robust. That means it should be not sensitive to the rest of the universe. Because, for example, you want to get something at some point maybe for commercial applications, and it should be relatively insensitive to the environment and things like that. So for all this application, it's really important that you have good methods to control the quantum state of your system. And with this, I came to my last part, really how to control the quantum system. And this is something a lot of groups are really working on new methods to find new ways for this stable and robust control of quantum mechanical systems. And this is something we are also doing here at UCC. This is, well, I do it, my PhD student, and David Rear, you all know, he's also working on it. And of course, we have also a lot of co-workers around the world, like in Spain, in Bilbao, Toulouse, in China, Dijon, who are also working on this. And as I said, we are not the only group working on this. There are worldwide, there are a network of groups really looking at this question of control of quantum system, because it's really important for all these applications. And just give you an example. A very simple example. Assume we have a trap. The blue one is something like a dipole trap. Let's assume it's simply a trap, a harmonic trap. The red one is a wave function of an atom. We have ultracold atoms. I told you before, they don't behave like billiard balls anymore. for the motion, you have to take into account the wave function, the quantum mechanical wave function. And the goal is we want to move the trap from here to there. Like a glass of water, well, this is not very good, but nevertheless, you want to move it from here to here. The important point is, there should be no excitations at the end. So if you move it at the end, your water should still be in the glass. There should be no fluctuation. It should be at rest. And this is what we want to achieve. And one way to do it, well, you know how to do it with a glass of water. I just start here. I move it very slowly from here to there. If I do this very slowly, everything is fine. And the same works in quantum mechanics. So if you move the trap, now with your quantum particle in it, very slowly from here to here, this is also called adiabatic transport. Then there's a theorem in quantum mechanics, this adiabatic theorem, which tells you if you do this infinitely slowly, everything is wonderful. It works perfectly. Let's look at a movie. For example, here in black, this is the trap. The red one is the wave function of the atom. And this is just a movie. We move the trap very slowly from here to here. And we will see in a second that at the end, the wave function is really at rest. But you immediately see a disadvantage of this. This is really slow traffic. This really takes time. The advantage is, of course, it's very robust, but very slow. And if we just do it faster, you see it here, just move the potential faster, it doesn't work. At the end, our atom is not in rest. You see its wave packet is oscillating a lot. So simply doing this adiabatic transport faster doesn't work. Adiabaticity breaks down. And so the key idea is really to find new methods for fast and stable manipulation of quantum states, in this case for fast and stable transport from here to here. And I will just show you the result, how you can do it really faster and still stable. Like this. You move first the trap very fast in this direction, then go back, and then you go to the final position. Let's look at maybe again, like this. And it would also work with a glass of water. If you move it fast like this, back like this, at the end your water would be roughly at rest. I will not try it because experiments never work and it will be a little wet and things like that. But in theory, it should also work with water. Okay, so here, in principle, this is something like you can find ways to do it better. And I would also show you a second example, which I will go a little bit more into the details here of the mass. And the second example is the internal state control. You all know if you have an atom, hydrogen atom, there are internal states. And here we restrict only on two states. We call them 0 and 1. And this is a way to represent a qubit. We had seen before this quantum computer, you don't have a bit anymore. A qubit is a quantum bit. This time, your atom cannot be in the state 0 or in the state 1. No, it can be in every superposition of the two states. And one way to represent this superposition, you can plot it on the Bloch sphere. Bloch sphere is a sphere, and this red one here is something like a vector. It points to some point on the sphere, and the north pole corresponds to the ground state, state 0. The south pole corresponds to the excited state, state 1. And every point on this sphere is a valid quantum state. And the key idea is here to do population inversion. You want to control this internal state, you want to compute with it. And one example is, for example, your atom is in the ground state, it should be in the excited state, in state 1. And how to do it? Oops. One possibility is the simplest way. We can shine in some light with some constant intensity, and where the energy of the photons equals the energy of this transition here. We shine it in for some fixed time t, capital T, in such a way that this product is pi. This is why you call this thing also pi pulse. And what happens if I really do this? Let's look at the Bloch sphere. What happens with this red vector? With time, it just moves from the north pole, from the ground state, to the south pole, which corresponds that the atom is excited. Fine, great. This works very nicely. Nevertheless, there might be a problem, because as I said, it depends on the environment. Maybe the experimentalists are not very good, really. There's some fluctuation in the intensity of the laser. You cannot really control it exactly in such a way that, for example, this is slightly smaller than pi. So what happened then? Let's look again at the movie. We start from the north pole, but because the intensity of the laser is fluctuating, it is too little, we don't, at the end, don't exactly end at the south pole. It doesn't work anymore, the scheme. At least it doesn't work perfectly. And the key idea is now to find better schemes. Find better methods how to do this, and just give you a brief outline of the idea how one can do it. This is the Hamiltonian of this two-level system, which is a 2 times 2 matrix. This is the Hermitian matrix. This is the most general form. And we want to solve the Schrödinger equation. This is the corresponding Schrödinger equation with this Hamiltonian. And we put in an ansatz for the solution. This is my ansatz for the solution. This ansatz depends on auxiliary functions, alpha, theta, and gamma. And if I simply put in this ansatz in my Schrödinger equation, then I find that these auxiliary functions have to fulfill these 3 equations. So just to summarize, normally these objects are given, this delta and this omega. What is it? The delta is practically the frequency of my laser I'm shining in. The omega is practically the intensity of my laser. So this is given in the laboratory. Then I want to solve the Schrödinger equation, which means I have to solve these 3 equations to get these 3 auxiliary functions. Then I put them here in, and I get the solution. This is the standard direct way how you would solve the Schrödinger equation. Okay, just 1 minute, and I'm ready. And have you taken into account that we started 6 minutes later? Okay, and well, this is the standard way, as I have explained you. But the key idea is now, do everything the other way around. Do some inverse engineering. Assume we don't care about the physical potential. We start with the auxiliary functions. We just choose the auxiliary function how we like them, but we choose them in such a way that they fulfill the boundary conditions. And by this boundary condition, we make sure that this vector you have seen starts at the north pole, and at the end, it's really at the south pole. So this makes sure that whatever we get out, it will work perfectly. And then we start with these auxiliary functions, and then we rearrange these equations to get explicitly the physical potential. This is a nice way. We just start with the solution. We fix the solution of the Schrödinger equation, and then we do some inverse engineering to get the physical potential, which I then have to tell my experimental colleagues they should do this in the laboratory. And I'm now coming to the end. Just gives you an example what will come out if you do this, and you can optimize it to make it as stable as possible, find the most stable solution. And this is optimal concerning systematic errors. These are the physical potentials here versus time. And let's now look with this scheme how our vector moves. And we see it moves different from before, which is not surprising. Okay, it moves different. What is the advantage of it? Well, if we look at this, this is the probability that my scheme works perfectly. And this is something like the strength of the error in which my laser is fluctuating. And we see the simple pi pulse in green. If there's some error, it relatively fast breaks down. The probability goes down. But this scheme we had seen before, this corresponds to the blue curve. It's much more stable concerning fluctuations. So this is just to give you an example really how this works, what is the advantage. You get schemes which are much more stable. With this, I would like to come to the summary. I told you a little bit, gave an example of a quantum system, which were ultracold atoms. I showed you why do you want to have ultracold atoms, what are possible applications, which are really very close. This quantum key distribution, this you can really buy. But for all this application, it's very essential that you have very good methods to control your quantum system. I briefly showed you how these methods can be derived. Well, and with this, I would like to stop and thank you for your attention.